actually form a fairly nice pattern. Okay, so what I've done here is I've drawn these regions here, these kind of triangular shaped regions. Turns out that the pre-image of any point, there's always, for any point W, there's a pre-image in every single one of these. Okay, there's a pre-image. So you can see what's happening is that the pre-images aren't converging all over the place, they're converging to the point 1. Yeah, because they will be 1 in every single one here. Okay, so eventually they'll get to 1. Okay, and this is, I'm not going to talk too much about this, but this is because the conformal mapping can be considered as a conformal mapping from a Riemann surface onto the multiply connected domain. Okay. So those things, you might wonder, you might think, well, those regions are a bit weird. Okay, those regions are a bit weird. They look slightly triangular, but they're not really triangles. And that's because they're triangles in the hyperbolic plane. Okay. In complex analysis, when you're looking at functions in a particular open set, it makes absolutely no sense to think about Euclidean geometry. Okay, it doesn't make any sense at all. As far as you're concerned, if you're a point in that domain, you can't see further than the boundary. Okay, so that boundary should be at infinity. Okay, that boundary should be infinity. And the way we kind of work with that, the way we look at that is by considering something called the hyperbolic plane. Okay, so the hyperbolic plane mimics hyperbolic geometry, which is different from Euclidean geometry. If you take, I think, triangles in hyperbolic geometry have interior angles adding up to less than 180, okay, which is obviously different to Euclidean geometry. In this example, and it turns out that it makes much more sense to look at hyperbolic geometry. Okay, actually, it makes no sense to look at Euclidean geometry. Okay, so each of these triangles is actually what we call a hyperbolic triangle. Okay, hyperbolic geometry is a much more natural way of looking at things, but also just because one of the things is that hyperbolic geometry is conformally invariant. Okay, actually, then that's quite humongously important. Okay, so in hyperbolic geometry, you can still measure the distance between one point and another. Okay, I'll call that dh of zw. But you should think of, if I go back to that, where is it? If I go back to this diagram, okay, think of these triangles as just triangles in the hyperbolic geometry. In hyperbolic geometry, every single one is the same size. Okay, they're exactly the same size. So the fact that they look like that to you, that they're getting smaller, is irrelevant. Okay, they're not getting smaller; they are exactly the same size. Okay? It's just that the smaller ones are closer to the boundary. Yeah, and if you think of the boundary being at the point at infinity, then the boundary is really far away, so your triangles look small. There you go, hyperbolic geometry in a nutshell. Okay. Okay, so let's go back to these triangles. So we know that there's a pre-image in every single triangle here. Okay, so we need some way of understanding where these things are. Okay, but we can use hyperbolic geometry quite well because we also, with hyperbolic geometry, there are mappings of the unit disk into itself called automorphisms that essentially just interchange all these triangles. Okay, they interchange all these triangles. If you pick one triangle, there's an automorphism of the unit disk. Okay, that maps it to any of the others. Okay, so it keeps the disk where it is, but it maps that single triangle to another triangle.
How do you define distances actually?
Well, the distance, there's a formula, but you can use, the geodesics will be circles orthogonal to the unit circle, or radii, okay? But the distance on the radius, okay, the distance on the radius is the logarithm of, the distance from 0 to the point z on the radius will be logarithm of 0, the logarithm of 1 plus mod z over 1 minus mod z. And then everything else will come from, you can just map any other 2 points to those 2 points and work it out. It's not difficult, but I'm not going to recite it. But it's that kind of, there's a formula for it, you can work it out, it's no problem. Okay. So each of these triangles is the same thing, but more importantly is that it's like they're generated by all these automorphisms. Okay, so these automorphisms I'm talking about mappings that map the disk itself. They're also conformal and one-to-one, but they're kind of these bland conformal mappings that I was talking about with R3. Okay, so these mappings are one-to-one, we call them automorphisms. They keep hyperbolic distances the same. Okay, so if one of these automorphisms moves Z1, Z2 to W1, W2, then the distance between W1 and W2 is the same as the distance from Z1 to Z2. Okay, it's invariant. Okay, that actually makes it an isomorphism, but I'm saying too much about the different words. So in this example, you can state explicitly, although please don't check this because I'm not absolutely 100% sure, but the function, I think it's g of z is z minus a half over 1 minus a half z. Okay, fairly straightforward function. This maps the unit disk into itself, okay, and it maps those triangles into one of those triangles into another triangle. Okay, turns out that's all you need. Okay, to map any of these triangles into any other triangle. Okay, so if T and T dashed are any two triangles, then T dashed is the image under a number of compositions of G. Okay, you might need to interchange the T and T dash there. Okay, depending which way it goes around. Yeah, yeah. And I wasn't going to write for same. But the idea is that you've got a single generating automorphism, and it maps all the triangles, different levels of composition, different iterations of that function map different triangles to different triangles.
I mean, that hyperbolically, the boundary of the previous picture looks a bit like Z, the set of integers, because it goes two-way infinites.
It is exactly that.
So it's something, okay.
It's exactly that. This is a particularly simple example of what's going on. Okay, but you're right. If you think of this, if you know what I'm talking about, then we're talking about a group here. Okay, oops, I won't do that yet. We're talking about a group here. Okay, so you've got a group of these functions. Okay, and it's a group under composition. And you're right. It is Z. Okay, it's also homeomorphic to Z. Okay, which is a particularly nice and simple example. So this function, it turns out you've got this really complicated mapping from the disk onto the unit disk without the point 0, and it looks difficult. Okay, it looks difficult to understand until you work these things out, until you realise what's going on. So if you know what the function g is, you know where every single pre-image is. Okay, because every single pre-image is now in the orbit of this group. So it's a point where g of z is equal to whatever. Yeah, it's where the group is converging to. So that's why all pre-images converge to 1. Okay. There's a lot more you can say as well. Because this is a particularly nice type of mapping, they actually converge in a circle towards 1. Okay, called a horocycle. Okay, not a horocycle, a horocycle. Okay. That's of course a very nice simple example. Okay, that's a very nice simple. That's not always true. Okay, in general, multiply connected domains, you can do the same thing. You don't get triangles, I'm afraid. Okay, you get something more complicated. You get something a little bit more complicated. This would be something like this. So again, this is the same kind of thing. Okay, so you've got the red polygon, hyperbolic polygon is just the name. Every single other one is the image under a particular automorphism. Okay, so they're all identical. Okay, and this is obviously not measured or anything like that. Okay, so please do not check it. I tried to get the right bits in the right place, but I can't guarantee. Okay, but this is slightly weird because you've got the corners of the polygon are at infinity. Okay, so you've got 4 different corners at infinity. You've got this massive gap here. Okay, this massive gap in the polygon there. Okay, so they're all a bit weird. You got to think. The way it works is that every one of these polynomials is mapped in a one-to-one way onto your multiply connected domain. Okay, so it's like you're separating the original disk into bits where you can have one-to-one mappings. Okay. But more importantly than that, the idea is that you know that all of the pre-images are actual compositions by functions in this group. Are part of the orbit of this group. Okay. Right. So just to summarise, any multiply connected domain has this kind of tiling. Okay. This kind of tiling where the polygon is the image of every other one under an automorphism, and this set of automorphisms is a group. Okay. It's called a Fuchsian group after Fuchs. Okay. Automorphisms in general don't change hyperbolic distances, so it's like every single one of those images is identical to any other one. Okay, not just in shape, but in any 2 distances stay the same. Everything stays the same, really. Okay, and in terms of our mapping, every single one of them is mapped to our multiply connected domain. Okay, so it's a little bit more complicated than simply connected domains, but if you kind of look at the Riemann surface structure, the Fuchsian group structure, then you can understand a little bit about what's going on. Okay, so Fuchsian groups are almost a completely separate subject to composition operators. Okay, there has not been a link between them before. Okay, so a lot of what they know about Fuchsian groups has never been applied to what we know about composition operators. When you study Fuchsian groups, they have this thing called the Poincare series. Poincare series is this thing here, which looks complicated, but it's an important automorphic function. It doesn't change. It's one of these functions that doesn't change. It doesn't change when you change ZW to G of Z, G of W, or something like that. Okay, so it's a sum over your Fuchsian group of e to the minus s. And again, this hyperbolic distance between Z and G of W. Okay, so this is called the Poincare series. It's massively important in Fuchsian group theory because it turns out this thing only converges. Okay, the convergence-divergence thing mirrors the Hausdorff dimension of part of the boundary. Okay, part of the boundary. And that was a fairly celebrated result from the mid-90s. There's also a lot more going on with the Poincare series that I won't talk about, but as you'd expect, it's something to do with the Fuchsian group, the dynamics of the Fuchsian group as well, okay, and the underlying hyperbolic structure of what's going on in there. Okay, but I won't go into too much detail. Okay, yeah, I've got 2 more slides. There you go, that's decent. Okay, so the Poincare series. The Poincare series just kind of it kind of incorporates all this kind of information about your group. Okay. Right. So this is what I finally got to where I wanted to be. Okay. This is why we're looking at these 2 things. Okay. It turns out that the Poincare series and the Neverland accounting function are essentially the same thing. They're essentially the same thing. So this function that measures the dynamics of the Fuchsian group turns out to be the same thing that we're looking at for the Neverland accounting function. Okay, so on a finitely connected domain, then the n phi of w is equal to the Poincare series, or approximately equal to. Now this was a result that was proved last year. It's just been published. But it links for the first time these 2 areas. Okay, these 2 areas. What it means is that for Z close enough to the boundary, you can measure, you can estimate the Poincare series, and then that allows you to essentially work out have a much clearer understanding of what when composition operators are compact for multiply connected domains. Unfortunately, the final result is a bit of an anticlimax. It turns out that if you take a simply connected domain and remove n points from it, so that's your kind of standard multiply connected domain, then and suppose phi is your function mapping the disk to the multiply connected domain, and psi is the function mapping the disk to your simply connected domain. Turns out that C phi is compact if and only if C psi is. So after all of that machinery, turns out that removing points from a simply connected domain does not affect whether or not your composition operator is compact. It's all to do with the boundary. And the machinery to get there is quite a lot more involved, though, obviously. Okay, I'm going to leave it there, I think. No, any phi. So D0 is the simply connected domain.
Yeah.
You remove D is without the point. So the compactness only depends on the simply connected bit. If you remove points from the phi, so it's not any phi, any psi. It's just any. Those two functions basically. Okay. Now the simply connected, it's useful because the compactness of simply connected domains is very, very well understood. Yeah, very well understood, because you have very nice geometry of the boundary. There's books and books and books written about the boundary of univalent conformal mappings. Okay, but very little is really understood about multivariate conformal.
But then this is a great step forwards, because it's saying that one is
I think so.
only if the other one is. So it's saying you can extend,
Yeah.
well, not exactly everything, but it's
No, but it is.
an insight into
Yeah.
this.
And this link between the Poincare series and the Never-Linda function I can't find anywhere where that's written anywhere. So I think that's probably. The Never-Linda counting function comes from an area of maths that's not really to do with composition operators. So there are applications of that as well. Yeah.
You say linked, but you only have an approximately equal in your theorem one. What's going on?
That's good enough. That's good enough. Yeah, I mean, I only have a. Yeah, that's good. That is good enough. What are you talking about? I mean, it's not approximate. I mean, it's bounded above and below by constant multiples of.
That's what I was asking.
Yeah, and but yeah, that's it. In analysis, that's all you need, you know, right?
So what does this approximation mean? So they can any error bounds? Or?
No. It's more about the growth of the Never-Linda counting function that's important. The Poincare series is more. It's easier to get a handle on, okay? Because for the Poincare series, you're talking about iterates, okay? Iterates of a group. So they're fairly well understood, and it's about the dynamics as well of the group as well. Okay, so that's much better understood. And the fact is that the Poincare series has been used a lot, and it's been part of a lot of important research in the last 20, 30 years, say. Okay, because people realise that it is so linked to the structure. That these function groups are really talking about Riemann surfaces. Okay, and it's more about the hyperbolic structure of the Riemann surface and understanding that. So it's a bit around time
So what kind of machinery you use to prove this kind of theorems? So area like analysis, algebra, or
everything. I think we start with I use complex analysis to look at the boundary behaviour, but there's a lot of group theory in there, so algebra in there as well to prove that as well. I'll just give you a copy of my paper. I think I brought it if you want to read it. There's a lot of machinery to do with function groups, because they're really interesting. Yeah, they're really interesting, and understanding this limit set. I mean, the other thing I didn't mention was this where I talk about limit set. In something like this, you've got the red domain is being mapped into every single other one. So points in this one don't converge anywhere on the boundary, they converge to a whole big set on the boundary. Okay, so so they don't have a clear, they don't converge to, the example of this one, every point converges to 1, no matter where you are, because there's 1 in every one of those domains. But things like this, they converge to a whole set on the boundary. And that set mimics, it looks like a fractal set, it has, it looks like a Cantor set or something like that, so it has a dimension between 1 and 0. Okay. And the Poincare series only converges for s less than the dimension of this set. Okay, so this, it's all linked together. It's all linked to the dynamics, the kind of the kind of eventual behavior of the Fuchsian group.
So I don't know the connection between Hardy spaces and Hilbert spaces. Can you do this sort of stuff?
Well, the Hilbert space is a general definition of a space, isn't it? So
Yeah.
the Hardy space is an example of a Hilbert space.
Okay.
Yeah, it is, yeah. So it's an example, but a Hilbert space is just a vector space, isn't it, within a product, essentially. So the Hardy space is one of those, but it's not.
Okay.
Yeah, there are other Hilbert spaces that you can do this kind of thing on.
Okay.
Yeah, but it's just an example of one.
Okay.
Has Barney gone?
Yeah,
All right.
Okay, he's teaching actually. He's
Oh, is he?
He skipped some teaching to come.
Oh,
Okay. All
tea,
right.
coffee then maybe?
Yeah. Thank you very much.
Yeah, thanks a lot.